So now that we've talked about index notation and that we can start writing a lot of vector calculations a lot more efficiently, now we can start proving some vector identities and prove them a lot more efficiently than we could before. So you probably learned in multivariable calculus that the divergence of a curl is always 0. This is a good thing to have memorized. And if you proved it, you probably proved it by writing out every single term and commuting the partial derivatives and showing that they canceled. You've got about 6 terms that have to cancel here. That's doable, but it's long, and it's going to save you a lot of time and effort in your homework if you can do things like this more compactly, especially when it gets even more complicated. So let's write this out. I have a divergence, so that means I take partial derivative of part I of vector component of part I of whatever this is, and the repeated I means that these are summed together. But I'm taking the ith part of a curl, so I'm going to write that out with the Levi-Civita tensor from last time. So I am taking derivative of part I of, that's Levi-Civita tensor I, j, k. The first one is for what part of the final vector we're on. The second one is for the first vector I'm crossing, which in this case is j, and k is for the second vector I'm crossing, which is v. So we see that these indices are summed together. This j of the Levi-Civita is summed with that j, and this k in the Levi-Civita is summed with that k. I'm going to rewrite this to make this all a bit clearer. So I have my epsilon ijk. I have partial of I, partial of j, then v of k. So I have 2 partial derivatives right next to each other of 2 other indices. Now something should look familiar from the problem from the last video. And the last one, I had 2 vectors next to each other with the same index, and I swapped the indices. These were symmetric. On the other hand, if I swap the I and the j here in the Levi-Civita symbol, they're antisymmetric. The same trick is going to apply here. So the I and the j right here are antisymmetric, while the I and the j over here are symmetric. Every time this comes up, it's going to be 0. So I wrote that out more explicitly last time. I'm going to do this with slightly fewer steps. So I am going to swap the I and the j in the Levi-Civita symbol, and that gives me a negative sign. Then I'm going to commute these partial derivatives past each other. That's totally fine. I'm allowed to commute partial derivatives. And then all of that is times the k part of the v vector. But my repeated indices, like the j to the j and the I to the I, this index is just a way for me to keep track out of lots of terms. I could write my sum over j. I could also write my sum over I. The name doesn't really matter. All terms are going to get represented in this sum, whether I call it j or whether I call it I. Now, I can't switch that anywhere. If I switched this I to a j, but didn't switch to that one, that wouldn't be okay. That would mess up the system of my sum. But here, it's totally fine for me to rename things. That just means that I might be adding up the terms in a different order. So if I rename and rename the I and the j, I get the negative epsilon ijk partial I, partial j of vk, which is the negative of what I started with. So this has to be equal to 0. It is equal to its own negative, and there's only one thing that does that. So, same trick as last time. The renaming is going to feel weird. It's going to feel like cheating, but if it still feels weird to you, go ahead and write this out with every term, and you're going to see that they cancel with the partial derivatives commuted and a negative out front. This is just a way to systematize that, what you would do the long way, and do it all in one line. So this one you could write out the long way. Let's do one that's a little more ambitious. So in this one, I am going to take the curl of a product. So I'm going to have a function f, and then a vector field a, and both f and a are functions of position. The curl is going to apply to both of them. So in other words, I need to do product rule with a curl. This is one of those vector identities you can look up in the back of Griffith's electrodynamics, and this is how you can derive it for yourself without doing horrible amounts of cases. And a lot of the Griffith's electrodynamic identities you would not be able to guess unless someone told you. But here, the form is going to become pretty obvious. So I'm going to apply the curl to this. So this is a vector. I'm going to talk a vector component I, which means when I write this as a curl, I am going to put the vector component right here. I am talking about the ith part of this vector, then j and k are going to get summed over. I want the jth part of this vector, which is going to be in a partial derivative, and then I want the kth part of this vector. So that's just going to be a normal f, then the k component of a. F is whatever. So I doubt anyone knows off the top of their head how curl is supposed to apply the product rule. But this right here is just a normal partial derivative. And we can do product rule with partial derivatives. That part is easy. So I'm going to write that out where I still have this epsilon hanging out front. But now when I apply product rule, I could take a derivative of f, and then all of that is times my vector component. Or I'm going to have f like this and hold f constant, and then take the j derivative of vector component k. It's totally fine for me to apply product rule here. F is a scalar function, and the kth part of the vector is a scalar function. I'm not talking about the whole vector, I'm just talking about one part at a time. So let's try to get our terms straightened out a little bit more. I'm going to commute f out to the front because there are no derivatives acting on f. Now let's look at the index structure of these terms. This j is matched with that j. So we now need to treat this as a vector. Partial derivative of f, but as a vector, is the gradient. So this is going to be just like grad f. So we take the j component of that. And then this k is going to match up with that k. So A must be vector number 2 in our cross product. Vector number 1 of the cross product always goes with the middle component. Vector number 2 in the cross product always goes with the third component. I'm going to come back to that second term later. So when I use the rules of the cross product, that means this is my first vector. I'm going to have grad f. It's going to be crossed with A. And we are talking about component number I of that vector. Where this index better link up with that index. This is our free index. This is the one index by itself. So that tells us we're working with a vector, and that needs to be consistent. I need to be talking about the same one component I've isolated across the equations. Now over here, this part here is much simpler. This follows the form of curl that we talked about earlier. Vector number 1 is a partial derivative. Vector number 2 is vector A. So when you put all that together, that's just going to be f hanging out front times the curl of A, or well, part I of the curl of A, where again, this I has to be consistent with that I. So what I have at the bottom is now f times the ith part of the curl of A. And my i's are consistent. I'm talking about part I of my vector each time. I'm adding the I components together. So I can combine all of this in the bottom, and I see that the way I'm supposed to do curl, but product ruled, is, well, maybe a way you could have guessed. First, I'm going to apply the nabla whatever thing it is to f. So I get grad f crossed with A, where A is left alone, plus the version where now I leave f alone, and I apply curl to vector A. And that is how you do cross product, product rule with a cross product. So this is where vector notation and index notation really starts coming in handy. It would have been a little tricky to do this a priori, and it would have been really burdensome to write out every single term of all these identities and show them to cancel. But when we use index notation, we get to do that very compactly and just do that in a couple of lines. So this is a technique that you'll want to get used to for your homework in the first year.